This is a question out of the books, 1227. A former theological student. What a way to start a question. Now wait a minute, what happened to this student that he switched from theology to chemistry? I don't know. We could build a whole story around that probably. I'm not going to read the whole thing to you though. The real issue is, well, he's also in his 8th year of graduate study. That tells you something else too. Maybe he ought to switch to history or something. I don't know. Ooh. Biology maybe, I don't know. Huh?
Maybe back to theology.
Back to theology? Theology's not easy. That's like deep philosophy, specific philosophy. Anyway, so carried out the following reaction and, recognize what's going on here. This is just another vehicle for asking spectroscopy questions, right? So here's a reaction. You've got a starting material, you've got a product. Notice the reagents used and what the change ought to be, always. But poor guy, this is probably why he's still in his 8th year, or made it to his 8th year. He thinks he mislabeled. Now notice, he only thinks he mislabeled. All right, I shouldn't get caught up. But he thinks he mislabeled his samples of A and B. Which one's which, right? Which sample goes with which spectrum? That's the whole point. So I'm going to have to flip slides to get to the spectra. So you might want to write down in your notes the 2 structures before I flip to make it easier when you look at the spectra to say, I think that one belongs to this compound, I think the other one's the other compound. All right? So you guys got it written down, you ready to go? All right, 3, 2, 1, boom. So there are the 2 spectra. Minutes to ponder that, I'll say no more. So we got 2 reasons why the lower one is the starting material. The rest of you guys who are being quiet agree with that? Yeah, I get a lot of nods with that, all right. Anybody not quite sure what's going on? That's not a question anybody wants to admit to in a class this size. That's not something anybody wants to admit to in a group of 2. And I thought so. This is an old exam question, but in terms of model, one that you may see again, just not exactly the same one unless, I'm really rushed. It's like midnight on Thursday and I got to get this done for 8 o'clock Friday morning. But I told you about this kind of question because I like it, because it's simple, it's nice, and it's what IR does for us in our current state of affairs in organic chemistry. So here you got a choice of 6 compounds, and here you have a spectrum. And the question is simply match one of those 6 compounds to that spectrum. And again, I'll be quiet for a couple minutes, give you a chance to ponder that. There's a lot going on here. You've got 6 compounds, 1 spectrum. It's like, what do I do? Okay, let me tell you a problem like this. One, first, just say, hey, what do I see here? What functional groups are indicated? What's not indicated? That's always a good thing to observe as well, right? And so you take a quick scan here. I don't see an OH, right? Think about the 3 numbers that I've given you so far to use in the first pass, right? So you look at 3,000, that's a number, right? And what do I see? Only peaks just to the right, nothing just, was that a question? Okay. Only peaks just to the right, nothing just to the left. So now, having done that, I can look through my 6 compounds up here and say, is there anybody I can rule out? I saw a couple of nods. So what can I rule out just by the fact that I don't have anything just to the left of 3,000? I can rule out number 1, because it's a double bond. I can rule out number 4, because it's a double bond. And they're double bonds that have hydrogens on the carbons. That's important too, right? But I can rule out 1 and 4 to start with. Now I'm down to only 4 structures. Another peak that I told you to look at on first glance is look for the OH, about 3,300. Always a broad, strong signal. I look at about 3,300, nada, right? So now, can I rule out anything else? Well, I've already ruled out 1, but that's a second reason to rule out 1. I can also rule out 5. I'm down to 3. Process of elimination is fully legitimate in a question like this, right? So now I'm down to 2, 3, and 6 as my candidates. None of them have a carbonyl, but that's the third peak I told you to look for in an IR spectrum, right? So you look at about 1700 and there's nothing there, but then I don't expect anything there. But just to use the paradigm, that's what I would do. Look at 1700. So now I'm down to just 3 structures. One table that I gave you the other day on Wednesday and look for something in particular. And the thing in particular to look for is realize that 2 of my 3 candidates that remain are alkynes. They have triple bonds. Triple bond shows up in a very unique place. There are only 2 kinds of triple bonds you encounter in organic chemistry. That's an alkyne and a nitrile. CC triple bond and CN triple bond. Both of them show up roughly 2200. I look at roughly 2200 and oh boy, there it is. So now I see this and I know for sure that I've got either 3 or 6, and I can rule out 2 because 2 doesn't have a triple bond. Now what's the difference between 3 and 6? One of them has an H attached to the sp hybrid carbon. The other one does not. If there's a CH, there's got to be a peak. Okay? And that's the thing that lets you know which one it is as far as the spectrum. Now, I haven't told you, I don't think, where an sp carbon hydrogen bond will absorb in an IR spectrum. Have I? We haven't talked about that. No, he says. I can count on you. Anyway, think about what's been happening. Let's see. sp carbon to H, sp2 carbon to H. Where would sp carbon to H be if this is really a pattern? Still further to the left, right? And in fact, they show up at about 3300. But they're a CH, not an OH, so there'll always be a very sharp peak at about 3300. And when I say about, I mean about. You know, it can be plus or minus 100. All right? So you didn't know that, and that wasn't, I don't think, part of that table the other day, but now you do. Now you do know it. Quickly, write it all down, right? So you look there, that would be the last thing to do. Look there, I don't see a CH. Therefore, it's got to be 6. Or no, it shouldn't be X on that, it should be circling it. It's got to be 6, right? You guys got that? You okay? Well, yeah.
Does the CL make an impression anywhere on that? Or no?
The CL?
Yeah.
Yes, it does. And that's often very hard to actually pick out. Usually it's down in this region somewhere, and it may be part of what's going on here. Carbon halogen bonds, we usually don't bother talking about those here. Usually, and then they are usually only a few hundred in terms of their value. Okay? So let me sum up that paradigm. Oh, I'm sorry, yes.
Wouldn't the triple bond, the carbon triple bond also be affected by the chlorine because it would make the intensity a little bit higher?
That,
Or no?
yes, probably true. Probably, yes. It would certainly be creating a partial positive charge here. That would undoubtedly have an effect on what's going on there, yeah. Anything else? All right, so let's sum up this paradigm for a moment. So you look at a problem like this. I guarantee you the first exam will have something like this. Remember those numbers. You really got to do it. This is one of those times, you know, find the problems in the book. I got a couple of, I didn't put them in the library, but I did put, what was it, 2013 is on the website, D2L. So you can see exams there. But I can put the book back into the library so you guys can see whatever is still available. But when you look at a problem like this and you got to solve it, well, what I just did there now, modeling hopefully for you, is fine. And when it comes to it, give an explanation for your choices. I'm not looking for war and peace here, right? In fact, on exams like this, usually the more you write, the less you know. Just a hint, you know, and you guys will probably admit or realize that yourselves. A little bulleted list right here. I kind of don't, I appreciate the fact that people look through the spectrum from left to right and they say, okay, OH, and they write it down. Okay, CH, okay, write it down. All right, C double triple bond C, write it down. And that's okay, but it's not organized. And a little harder for me to look through that and say, oh, well, this is what helped you come up with the right answer. Something that really does help is you write here or wherever the space happens to be. Usually on an exam it's actually under it. I think it's 2. Or even just take 2 and circle it. All right? And then you make a short bulleted list that has the key points as to why you know it's 2. You know, C triple bond C at 2200. No. C sp carbon to H at about 3300. That's it, right? 2 reasons why that one happens to be number 6 and it can't be any other. The other approach, which is a little more lengthy, is to actually write down, I know it can't be 1 or 5 because there's no OH. You can give me the process of elimination, that's fine. It just usually tends to be longer. So when you're working on problems in the book, or you go and you find the old exams and you're thinking about what's going on there, and ask yourself, what would I write down? In real short phrases, but clearly, that it rules out all the other compounds. It means it's just this one. Right? That's what you got to do for me on an exam setting. Okay, and I really appreciate just short bulleted lists. I go down and say, yep, great, you get 10 points. Or, you guessed wrong, you gave me 3, and you totally missed this fact, but you got that one, and so I give you partial credit. Okay? So just think about that when you're working on problems in the book, or old exams, or getting ready for the quiz, and I'm about out of time. Any other questions or anything? Okay, see you guys next week.